Hello everybody, hope you're doing well and thank you for joining us for another video. Today we are tackling the big claim of flat earthers, that according to them, space can't exist, that you can't have gas pressure next to a vacuum without a physical container because otherwise the atmosphere would be sucked out into space. However, all of that seems to be built around several misconceptions. For example, if you take a container and you suck all the air out of it and then you open the lid, the air will rush in. So flat earthers argue that atmosphere next to space without a barrier would cause that same effect. Not quite the case. And later on I will show how we can get gas pressure next to a vacuum, but first, let's get some basic details straight about what gas pressure is and how it works. Nothing too complicated though, relax, just the kind of thing that you'd learn in high school, or on brilliant.org. Who have hundreds of classes on all manner of science, maths and computing. They even have classes on how gas pressure works. I'm currently working through their section on astrophysics. In fact, I've just come up to their class entitled The Round Earth. I wonder what that could be about. Their classes run through the principles of a topic and then quiz you about it as you go. Don't worry though if you get a question wrong, because they give you a detailed explanation on how to get the correct answer next time. And if you get the question right, then you earn experience points which go towards advancing through their leagues. I've made it all the way up to their Einsteinium League. And if you'd like to come and join in, then head on over using my link in the description to not only get a 30-day free trial, but you'll also receive 20% off an annual subscription. Gas, like our atmosphere, is made up of tiny molecules. And these particles are constantly on the move, even in an airtight box. If you take a box, seal it up and leave it on the side, the air molecules inside will still be moving because they have energy. These moving particles will inevitably crash into things, and just like anything that crashes into something else, when they do, they will exert a pressure force on that object. Now, with air molecules being so small and having hardly any mass, the pressure that gets exerted from a single molecule is minuscule. However, if you have enough molecules hitting a surface at the same time, then the total pressure becomes more and more noticeable. For example, the air pressure near sea level is around 14.7 pounds per square inch, meaning take a square inch of any surface there and the air will be exerting 14.7 pounds of pressure against it. Now, there are two ways that we can vary the pressure. We can change the density of the air or the temperature of it. If we increase the density of the air, we're adding more molecules of air into a given space, meaning more molecules will be hitting that particular square inch of surface, so the total force exerted on the surface will increase and thus we will have a higher gas pressure. Or we could also reduce the volume of space available to the same number of molecules, which is also increasing the density. If we were to have kept the density of molecules the same but instead increased the temperature, then the molecules would then have more energy and so they'd be moving faster, which would then raise the force that they would exert and thus increase the pressure. Kinda like a pressure cooker. So, gas pressure is merely the average force of gas molecules colliding with physical surfaces. Now, flat earthers have argued you can't have gas pressure without a container, but removing the container doesn't mean that the air that was inside no longer has pressure. It means the air has equalized to match the ambient pressure surrounding it. So if you take a brand new packet of balloons and you take one out, the balloon isn't inflated, nor is it sealed, but there is still air pressure inside. The air pressure inside will be equal to the air pressure outside, at about 14 psi. As you inflate the balloon, you still have 14 psi pushing against the outside of it, but the pressure inside will now increase, let's say to 16 psi. So we have a 2 psi difference between inside and outside. Now, the pressure difference between inside the balloon and outside won't shift by much due to the stretchy nature of the latex balloon. The pressure inside will push the balloon out and cause it to enlarge slightly, which will decrease the pressure until you put more air into it. It will continue to inflate in reaction to the increased air pressure inside until it reaches a point where the balloon itself just can't handle it and it will burst. But that doesn't necessarily come from putting more air inside the balloon. If we didn't inflate the balloon fully and we tied it off and placed it in a vacuum chamber, the pressure inside the balloon would remain the same, pushing outwards, but we could take the air out of the chamber, which would then reduce how much pressure was pushing back against the balloon, and the balloon would inflate just as before, as shown in this experiment by Simon Foster. Alternatively, we could increase the pressure in the chamber to more than 14 psi, and the balloon would deflate because there is now more force pushing on the balloon than there is pushing out. You may have also seen this if you've ever been on a plane and you've ordered any kind of sealed snack, such as a tube of Pringles. Other snacks are available. The lid of those always are ballooned out because they were sealed flat at ground level. But the cabin pressure at cruising altitude is lower, so the air inside has less force countering it. This actually relates to another misconception I see flat earthers sometimes make when they talk about like the ISS, especially following the Titan submersible disaster. Because they argue, how come you can't get a submersible down a few kilometers underwater, and yet you can have spacecraft with relatively thin walls surviving 250 kilometers high up in the vacuum of space? Now, vacuums aren't some magical force that pulls things away. They're simply areas with no matter in them. The pressure of one area is irrelevant. The key importance is the pressure difference between inside and outside. The Titan submersible was sealed at sea level, so the air inside was 14 psi. The water pressure at depth was 6,000 psi, meaning that hull was trying to withstand a pressure difference of almost 6,000 pounds per square inch. The air pressure on board the ISS is 14 psi. The outside air pressure is almost zero, meaning the hull is only having to withstand a pressure difference of 14 psi. For reference, a carbonated drink in a can has an internal pressure of between 30 to 50 psi, meaning that thin aluminium can is withstanding a pressure difference of up to around 36 psi without any problems. Anyway, flat earthers take this simplified behaviour of ideal gases and they extrapolate that if gas expands in all directions to fill the available space, then on a globe, in space, the gas would expand to fill space itself. Not quite the case though, because we have gravity to pull molecules back down. Now, I am not going into a whole gravity argument now, that needs a separate video, but suffice to say we don't always need a physical barrier to contain things. That small globe, for example, has no physical container holding it there and yet it's floating. What you need is forces for containment, and gravity is a force. I think flat earthers also have this conception that the globe atmosphere is simply atmosphere, 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 and then suddenly vacuum. And it's not. As you increase your altitude above sea level, the air pressure begins to decrease, and this continues the higher you go. This happens because gravity is pulling air molecules down, but then as more molecules are pulled down, the density increases, which increases the pressure. And then pulling more down becomes harder and harder. If you've ever taken a syringe filled with air and blocked the end of it and tried pushing it shut, you'll know what I mean. Pushing it at first is fairly easy, but as the pressure inside increases, you require more and more force to push it further and further in, because you always need to have more force on the outside pushing it in than there is force of air inside trying to push back against you. So the ambient pressure will then become less, and this continues the higher you go, with the drop in pressure actually slowing the further away you get from the ground. At sea level, the air pressure is 14.7 psi. If you go up 10,000 feet, it drops by about 4.5 psi. If you go up another 10,000 feet, it drops again, but only by 3.8 psi. Go up another 10,000 feet, it drops by only 1.9 psi. So the rate that the pressure drops slows more and more the further away from Earth you get. So as you go higher above Earth, the atmosphere doesn't suddenly just stop, it's getting gradually thinner and thinner. And space itself isn't where there stops being atmosphere. Space is merely an arbitrary borderline that we have put in place so that we can say, up to this point you are in Earth's atmosphere, and then beyond this point you are now classed as being in space. Kind of like the borderline between states. You go to Four Corners Monument, you can walk around in a small circle and cross between New Mexico, Arizona, Utah, and Colorado. Nothing suddenly changes, the space is still the same. Hell, not everyone can actually agree on where space starts. The popular reference used is the Kármán line at 100 kilometers or 62 miles above sea level. Now, this was put in place as a theoretical distance where air density is no longer sufficient for conventional aircraft to be able to maintain powered flight, or that any spacecraft at this point would begin to experience just enough drag resistance that it would no longer be able to manage one full orbit unpowered. But there is still air molecules beyond that distance. I mean, there's still air molecules up beyond the ISS, just nowhere near as many as we have down here. The ISS actually experiences a tiny amount of drag from those few molecules, which causes a very, very slow decline in their orbit, and every few months they have to do a small burn to raise the orbit height again. It's why old satellites eventually always fall back to Earth, because their orbit height slowly decays and no one does a burn to put it back in place. Now, the problem for flat earthers is, yes, if you remove gravity from the equation, then air molecules would be free to travel off into space, and then we would need a container. But, as flat earthers point out, ideal gas laws say that gas will try and expand in all directions to fill the available space. And Newton's first law of motion states that objects won't change direction unless a force acts upon it. So if there's no gravity, then there's no other force acting on the gas, it would be free to expand all the available space inside the firmament, and it would continue to do that until it reached an equilibrium, which would mean there wouldn't be a pressure gradient. Flat earthers keep asking to see an example of gas pressure next to a vacuum without a container, yet I keep asking to see a container with a measurable pressure gradient, and so far, nothing. However, using what we've learned about gas in this video, I am going to argue that I can technically show flat earth as an example of gas pressure next to a vacuum without a barrier. Right here. Because, as we've already established, gas pressure is caused by molecules colliding with other objects, and a vacuum is an area where there is no matter. There's no stipulation about how much area there has to be for it to constitute a vacuum. If I take a syringe and I push it shut and then I cover the end of it, there is hardly any air inside there. If I pull the syringe back, then the air pressure is now dropping to pretty much zero. There are still a few molecules flying around inside, and those will create a very small amount of pressure, but in between those molecules is nothing. So the syringe as an entire system might not be a perfect vacuum, but inside, we have areas of gas pressure right next to areas of perfect vacuum and no physical barrier separating them. There has to be nothing in between air molecules, because if I fill a syringe with air and then cover the end of it and try and squash it down, I can, because the air molecules still have space between them to move into. If there was no space to begin with, I wouldn't be able to compress the syringe. And space itself isn't a perfect vacuum. It's called a near-perfect vacuum. There are still air molecules whizzing around out there, they're just very few and far between. At sea level, the distance between air molecules is roughly 3.5 nanometers. Now, a nanometer is 1/1000th of a meter. Out in intergalactic space, the distance between molecules is more like 1 meter. So roughly 300 million times further apart. And an oxygen molecule is only 0.3 nanometers in size to begin with. To put this into perspective, if we were to take a bag of peas, with each one being 1 centimeter in size, and we say each one of those represents a molecule of air, at sea level each pea would be roughly 10 centimeters apart from every other pea. Out in intergalactic space, though, each pea would end up being 30,000 kilometers away from each other. But the point is that The globe isn't some solid wall of atmosphere that we live in and then suddenly there's a void of nothing. In reality, the majority of air that surrounds us now is in fact a vacuum. It just happens to be littered with air molecules that allow us to breathe. As we see with the P's, each P is a molecule of gas. Those molecules alone are what create gas pressure, and yet there is more areas of nothing between the P's than there are P's themselves. Which means every flat earther right now is surrounded by gas pressure that is directly next to a very, very small vacuum with no physical barrier in sight. And that, I think, is going to draw this video to a close. Thanks once again to Brilliant.org for sponsoring this video. If you've enjoyed it and you haven't already done so, then please consider hitting the like and subscribe buttons, and hopefully we'll see you in the next video.